Everyone has it.
We
So,
we didn't hear you.
so I would like to
Okay.
welcome you all to the to the annual meeting of the EFIP Working Group. Our first speaker for today is Mauricio. He's been very active in rewriting for quite a long time, also very active in formalization. And that is what his current presentation is going to be about. So, Mauricio, I'll leave the floor to you.
Okay, thank you very much, Cynthia, and also Carsten and all the EPIC group for this invitation. It's an honor for me, and I am very happy because of that. And well, what I will do is talking about a work in progress. We started several years ago on formalization of term rewriting and functional programming stuff in PBS. And I will try to make some emphasis on termination. Then the credit is also for Ariane Alves Almeida, Andrea Borges Abelar, Tiago Mendoza Ferreira Ramos, Ariane and Andrea alumni from the group, and Tiago is a current PhD student. They work hard in the formalization. Cesar Munoz, that moved recently to Amazon and was formerly in NASA. Mariano Moscato and Aaron Dutle from National Institute of Aerospace and NASA formal method groups in lab. Then I'll show you the plan. I will talk about the functional model we coined out to reason about termination of a fragment of PBS programs. And then I will move to the termination criteria we specify in PBS. And then I will discuss something that is really a confusion I have about, or we have about how to profit from termination criteria for time rewriting system to warrant termination of functional specification. That is our main objective regarding termination, using rewriting techniques to prove termination of functional programs. I didn't talk very much about what is PBS, but PBS is a proof assistant, and the specification language of PBS is a high order functional specification language that includes also subtyping and dependent types, and uses a logic that is based on a high order sequence calculus. Then we really restrict the analysis to the case of first order functional fragment of this logic. To motivate termination, well, deciding whether a functional specification is terminating or is in fact a functional well-defined object is not easy. In several cases, we have some confusion about that, and we have to do proof by hand, and it's not necessarily a thing aspect to be automatized for recursive functions or recursive objects. Then this is an example misuse of the arguments in the specification of the Ackermann function. This one is the Ackermann function, the first one. And the second one is not exactly the Ackermann function. No, the second one is a variant where we swapped the arguments. And swapping the arguments appear, we have the same function or something very similar, or you can say a digitation error. And this is not a function. This is a specification that defines an infinite loop. For the specifier, this is not so obvious. Perhaps for use, it's obvious. Also, I would put the example of the McCarthy 91 function. No, this is the McCarthy 99 function. Essentially, what we do is for numbers smaller than 100, we call nested recursive the function, adding 11 to the argument. And then when we pass the 100, then we start to eliminate the call and resolve the equation. Then it's difficult to count what happens because you are nesting recursive calls and adding 11. Then to count the number of steps, you need to be sure that this function terminates. Is okay, say elemental but not trivial combinatorial task. No, this is, for instance, the number of nested recursive calls that you will add for numbers smaller than 100, and the rest of the expression, that is the number of calls that you promote before you finish, and you obtain the 91 result, has to do with, okay, when you are, for instance, in 90, you move to 101, adding a recursive call, then you go back to 91, and then to 102, adding a recursive call, and so on. Then in this point, you maintain the number of recursive calls stable, but you use 23 steps until you come back to 91, and you eliminate the recursive call. Then it's not easy, and we have some variants here of the of this specification of the McCarthy function. We play the same game, n-10, like here, for n greater than 100. And we apply two recursive calls here of this m1 function, but plus 10 for the case that n is less than equal 100. And here we play the game in other way. We subtract 3 for n greater than 100. And we apply 3 recursive calls, adding 7 to the argument, if n is less equal than 100. In fact, this is a family of situations, as pointed out by Donald Knuth in his famous generalization of the McCarthy 91 function. And we have some cases in which this family of functions will work and will not work. In particular, the M1 will not work, the M2 and M will work. And we have a general theorem of termination of this family of functions, that this is one. No? Also, we extend the domain for integers, n and m, m strictly positive integer, and a, b, and c reals. And for these parameters, a, b, c, n, k, given as the function kn, the same game, n minus b, if n is greater than a, and m nested calls of k, adding c to n, if n is smaller equal to a. And this will define a total function. That means this will be terminating whenever this inequation holds, n minus 1 times b smaller than c. Okay, then This is the kind of situation in which we fail to automatize function. And because of that, we try to enlarge the power of automation of PBS, and we start from a very formal mechanism that was to specify this fragment of first order specifications in the specification language of PBS. And for that, we define a language computational model that is called PBS0. Okay, PBS0 is then a minimal first order functional language that has the following syntax. The expressions in PBS are either constants, variable, in a working type, and we have some built-in unary operators and binary operators. This N here is an index. And we have a branching instruction that is an if then else instruction with expressions and the recursive call. Then the initial model is a single function initial model, and this is inspired in the fact that this in the syntax of PBS we didn't allow mutual recursion. Then we are following the discipline that the analysis of a new specified functions assumes that all previous functions are verified as correct, well-typed functions. Then the analysis depends only on the new function we are specifying. Because of that, we don't need a name for the function in the recursive call. Essentially, a command that say, or an instruction that say rec. This is a recursive call of the function we are defining using the expression given here. Okay, and we work only with a type. Then we have to make some tricks in order to, for instance, implement functions that are binary. We need an engine to think about tuples of input and so on. This is an example of a PBS expression, if then else of 1, 0 BR, 1 up to, and so on. And look here, we have a recursive call for the result of the binary built-in operator indexed by 1 with the input. The variable is the input value. Okay, then this is what we have. And then associated to each PBS expression, there are the list of unary and binary functions and an interpretation, an element of the working type to be interpreted as false. Okay, then we have an example here. This is the Fibonacci function. We have the operator that check whether x is smaller than 2. We have a predicate x minus 1. We have minus 2, and so on. And then the Fibonacci is defined as if then else. We apply the unary operator indexed at 0 with the input variable. We answer 1. In the case this is true. Okay, let's see what is this. And in other case, we apply the indexed operator binary plus the recursive call for the variable plus 1 and the variable plus 2. This is the operator 1 unary is let's see, minus 1 and minus the second predecessor. Okay, it's a It's not that cryptographic as I explained it. And then we have to define for this language mechanism for evaluation that I call the semantic evaluation mechanism. This semantic mechanism is given in a predicative manner and in a functional manner. Then usually then we have to check whether a program that is a quadruplet, this is the expression, that is the kernel of the program, with input E evaluates to output O. And this is the expression that should be a subexpression of the program. We are evaluating currently. And the functional specification uses some natural number for the bound on the number of nested recursive calls. Okay, then let me show you what is the predicational evaluation. We are evaluating a program that is a quadruplet, right? We are evaluating in particular this subexpression of the program, of the kernel of the program. And with input E, we have output O whenever, okay, we check whether it's a constant, whether it's a variable, whether it's a specific operator, unary or binary. And we have to then evaluate the argument or evaluate the arguments in order to proceed with the, and what is interesting here, perhaps, is the recursive call. When we have an expression in the program that is a recursive call, then what we have to do is to check whether B prime is the output of evaluating this expression, and after that, we evaluate again. We come back to the expression that is the Wole program, the kernel of the Wole program, the F, to evaluate this output of the result of the evaluation of the argument, and so on. The other function of semantic evaluation is what we call the functional evaluation function. And for this case, we will answer either a none when we don't succeed under this number of bound of nested recursive calls. And this bound is controlled in the recursive call in the following manner. We evaluate the expression of the recursive call with the same bound of nested recursive calls. And when we succeed, right? Succeed means we obtain a value that is different from none, from this diamond value. And then when we succeed, we evaluate the kernel again of the function with this output value that is different from none. Then essentially we have two semantic definitions for this the evaluation of this program. And then using this semantic evaluation, we can prove some results like the functionality of the predicational specification. When this predicate has outputs O and O prime for the same expression of the program and the same input, then they have to be the same. We have also then the definition of termination under this semantic notion or semantic evaluation. For the predicate evaluation, we say that the program PBS0 halts with input E whenever there is some output such that the evaluation is true for this program with this kernel, input E and output O. And for the functional evaluation, we say that, okay, this predicate is true, or the program terminates with input E, whenever there exists a bound of nested recursive calls such that the functional evaluation using this bound of nested recursive calls provides something that is different from none. All right, then we have the definition of semantic evaluation, predicacional, funcional, and we have some properties like the equivalence between the both notion of semantic termination, the predicacional and the funcional, and all that is specified. Well, we have then what? A computational model for reasoning about functional specification. And the first question we have to answer when we try to formalize is whether this model is consistent with our intention. Then we start a project to show that, and Thiago is working in the formalization of that. And then we start to think about this as a computational model. I think it's a very academic work. Perhaps it's not interesting from the point of view of our main objective, that is using and improving the power of automation of termination in PBS, but for use as an academic institution, it's a very nice and interesting piece of formalization. Then we have a specification of what is called a multiple function PBS computational model, because using this single model, we have promised to show constructively Turing completeness. Turing completeness with the single function model is proved by existence. The composition of programs is proved showing that there should exist a function, a function direct that simulates this composition. Then with the multiple function, we have the power to talk about composition in a natural way. Then using this model, we provide things like the undesirability of the halting problem for the model, the Turing completeness of the model, the recursion theorem, the Rice theorem, and the fixed point theorems. All the interesting results related with a computational model, but with itself. I will go further on that. Okay, this is done as part of this theory, the PBS and CCG theories, that if almost 1,000 theorems, proven theorems, and the part from these theories related with Thiago works at almost 300 theorems, formalized theorems related with the Rice theorem, recursion theorem, halting theorem, fixed point theorem, and Turing completeness. Okay, then for some of the theorems, we fixed the built-in operators. We say the unary built-in operators are successor and the first and second projection, and the binary operators are greater than and Kappa-DOS that is used to encode and decode tuples of natural. The working type is the type of natural. Then, well, the Turing completeness is proved in a classical manner, showing that we can PBS zero define the basic operators, composition, minimization, and primitive recurrence. In fact, what we have is not a completeness, but the power of implementing that. We proved in one sense, in one direction. Then For the composition, we define an operator of composition, and we say the encoding here is complicated, but okay, I think I laid some links here in the foils, in the slides, so that you can see directly the specification. But essentially, we use the multiple function mechanism in order to add, to concatenate the programs and update the indices of the programs. So we can work firstly with a function, and then after we finish the evaluation of this function, we move to the other one in the multiple function. We build the constructor for minimization, and we will the constructor for primitive recurrence. It's interesting to say the working type is the type of naturals, but this is specified as is done in a classical definition of a primitive recurrence, in which you have a function and a family of functions that so that the first function is an n-ary function, and this family of functions are used as argument. How with this trick of encoding and decoding, okay, he worked with this listant in one direction and the kappa-2 in other direction. We have the inverse. This is a binary function. Then it's possible to specify the classical ideas for this, what we call the Turing completeness. The recursion theorem, then we have also nice specification of this recursion theorem. Essentially, we have to encode a prime function. We define what is a partial recursive function. We have a kappa p, that is a Gödelization of the partial recursive PBS0 programs. Perhaps I can show some part of the code here. Let me show you. Essentially, what we do is we have the variables program or identity program is Gödelized at 0. When you have a constant, you multiply by 5, the value of the variable, 5 plus 1. And I was with this classical trick, 5 plus 2, 5 plus 3, 5 plus 4, and so on. Then you use the module 5 in order to know whether you are talking about a constant, recursive call, and unary, binary, or if then else operator. That's the idea of this Gödelization. Okay, and was maybe is interesting to mention here. This is a version right defined, but is a semantic predicate, and we say whenever this is if exists a decider computable function if this function satisfies this predicate, then the predicate is the full set or the empty set. Let me, I have to say something here about the, okay, here is used the Gödelization. And what else was important here to think? No, let's go further to the next. Okay, for the understandability of the halting problem, what is interesting is that we don't need to fix the unary and binary operators because the power of this model is with an arbitrary set of unary and binary operator, it's not enough to decide whether a program that uses the same binary and unary operators halts. Then we have more flexibility in this case, all right? Okay, then this is what is interesting for the undecidability of the halting problem. And the specifications are always very plain. I can say that the power of the high order logic to discuss and formalize such theorems is fantastic. That is a little bit of propaganda about why we are doing that in PBS. Because the proofs are very natural and they are inspired in, for instance, the didactic of Zipser's textbook. For this one, we use the Floyd and Bagel's textbook, that is a classical book from the 70s, end of the 70s, and so on. For the fixed point theorem, we also let's see whether don't need to fix the binary and unary operators. Okay, then some work in progress is related with undecidability of problems that are not inside this family of problems related with the properties of the computational model itself. And we have to move to other models of computation. For instance, we are now working in a formalization of the undecidability of the post-correspondence problem, and also as a byproduct undecidability of the word problem for semi-2 system using the same ideas. Okay, these are problems that are not related with that are not related to properties of the models, and okay, if it's a nice thing, but in principle, what we have now using and reasoning about the same model, PBS0 as a model of computation, are these results. Okay, then it's all that to say that we have a consistent model. This model is formalized as a consistent model of computation, and our intention of using that to reason about the first order fragment of PBS makes sense. Okay, then let me talk a little bit about termination criteria. That is also part of this PBS0 theory. And I will use as a running example the Ackermann function. Again, this is the specification of the Ackermann function encoded in the language of PBS and encoded in the language of PBS0. This is the encoding of the list of binary and unary operators in unary operator to check whether m is equal to 0, whether a natural is equal to 0, and no more than that. Okay, then the semantic of termination implementing PBS is the one called Turing termination that consists in the generation of type corrected condition for terminations. And these are related with an statistical analysis of the program, checking for the conditions in the branching instruction, for the words in the branching instruction that led to a recursive call. Then what we have are triplets, right? Some conditions or accumulation of conditions according to the PEPs in the program, and the arguments of the recursive calls. And for this termination, what we need is, to prove is that after each recursive call, the measure of the parameters, or some measure for the parameters, decreases, strictly decreases. Then, for instance, for the Ackermann function, we have 3 conditions. one condition is to show that the measure of the formal parameters are greater than the measure of these actual parameters in this call. This is the blue one. M-1 is smaller than the formal parameters, M and N. For this recursive call, the same, okay? And for this recursive call, the green one, the internal recursive call, we have to show that M and N-1 is smaller than the formal parameters. Then the usual trick for the Ackermann function is to use some lexicographical order on the parameters, and that works. This is the measure we have to, we can use to show the termination for Ackermann using the TSS termination criterion. Okay, but there are criteria that are more, say, global, and we focus on the side chain principal derivation. This was coined by Leon Penn-Hamrad in 2001, and essentially the idea is that if every possible infinite computation leads to an infinite decreasing over a well-founded order, then the program is terminating. It's no longer a local analysis because we are not asking for a strict decrease after each recursive call, but we are thinking about the flow diagram of the execution of the program, of the function, and looking whether in a possible infinite computation, there is some strict decrease. Okay, then this was related with dependency pairs at some point by authors like René Thiemann and others, Giselt also. And what we have to come here is something like checking for the possible infinite computation and showing a decrement. This is also formalized in our system, the sidechain principle, but we enjoy this derivative technology from Manolius and Braun, presented in CAP in 2006, the Kelling context graph. Okay, the Kelling context graph builds the flow diagram of the program using the notion of Kelling context. Every Kelling context is a vertex, and there exists an edge from a Kelling context SI to a SSJ, other Kelling context. If this has a sequence, and having a sequence is the possibility to have a call SSJ after call SSI. Okay. And the nice trick from the Kelling context graph is that they allow a family of measure functions, and these measure functions are combined in the graph, in the Kelling context graph. Okay, then I will show the idea using the Ackermann function or running example. We have 3 Kelling contests for the Ackermann function, and the thing is that we can use the measures first argument and second argument and check whether these arguments, how these arguments change, how this argument can be compared during the execution. Okay, during the possible execution. Then, for instance, we lost a loop here because after the call 1, we cannot repeat this call because this call is done when n is equal to 0. And when n is equal to 0, we call the blue one Ackermann from the second argument is 1, and 1 is different from 0. Then this call might be automatically eliminated. Okay, when I say automatically eliminated, I'm thinking about the implementation as it was done. We can eliminate this loop because the system can automatically decide that this is not possible. But this may be redundant. Okay, some of the conditions might not be checked, then they are maintained here. But since this is redundant, if we can show that some combination of these measures in each possible circuit in this graph decrease, then the function is terminating. Okay, this is an implementation from Andrea Avelar that organized the idea in a more interesting way or more algebraic way. We use the family of functions, measure functions, and we encode the combination in quadratic matrices in which we decode the, I don't know whether there is a decrease, there is not a strict decrement, and there is the strict decrement with this tripartite algebra. And then the edges are decoded by decimal matrices. And how we check the combination through a trick that is essentially the expansion of this algebra, where the addition is the maximum and the multiplication is defined by, okay, when you don't know, when you are combined in an edge, these are not comparable, don't matter. The going to the other edge is, okay, they are not comparable. When you say they are equal and the other one, then you maintain the other one. And when both are decreasing, then you say it's decreasing. But notice that we go, what we win? We win that 0 times 1 is 1. Then we can enlarge this analysis when some of the parameters remains equal, and after some point is comparable, not essentially with the same parameter or with other parameters, with any order, because we are talking about a family of measures in the graph. Okay, then the idea in this algebra is that the decrement, the strict decrement in a PET is given by the positiveness of the matrix. Of the, okay, I say adjacency matrix because the idea comes from the construction of adjacency matrices in graph theory. And the positiveness means that you have an 1 in the diagonal. Okay. Then this is nice because using this structure, we can automatize the determination using the Kelly-Conte graph in a very ordered, systematic way. And okay, this was explained in this paper in ITP 2021. Okay. The idea is very simple, no? When you think about graph theory, because you have a bounded number of combination here. Every edge and every PET might have only, you have an algebra with 3 values, then you have n squared 2, n to the power 2, 3 n power 2 possibilities for each edge, and is also restricted because this graph is finite. Then you use some saturation method in order to check whether the function is terminating. Okay, then I move to the equivalence properties, and I am now short of time. In addition, then we proved that this type correctness condition termination is equivalent to sidechain principle termination, And this is equivalent to Kelling context graph termination, and this is equivalent to matrix-weighted graph termination. This is also formalized in the PBS theories and the SSG theories, and also presented in the CiteP paper. Okay, what we want? What we want is that usually you have a measure here that strictly decreases when you, after each recursive call, you have not this measure for this. You have the combination of measure and things like that, this global criteria. But this equivalence show the existence of the strict decrement. And then you can use that to build induction schemata for your proofs. You don't need to have the measure. Okay. Now I have not many time to talk about that, but our main objective or my main objective in this project as a rewriting person was to think about what to do and how to empower the automation of termination verification in a functional language like the specification language of PBS using term rewriting properties, and look into some papers from Arts, Gisel, and René Tim, and I saw this relation between the dependency pair criterion and the Kelling context graph from Manolius and Brown. Then we use this dependency pair criterion with Ariane. That, okay, I don't really explain too much about that because I know a lot of people here in this audience know that. The objective is trying to apply this mechanism in order to prove the termination or verify or warrant determination of a functional specification. And this was the work from Ariane, or this was the objective from Ariane, but in principle, it was not fulfilled because we have several problems. Now we are comparing, when we think about a termination of a term rewriting system, we are thinking about how the terms evolve. When we think about termination of functional programs, we are thinking about how the values of a type, of a working type, evolve. And this creates a very big problem. Then we have this formalization, but in the term rewriting system library, that is also part of our work, the formalization uses a classical counter position analysis. From infinite chains of dependency pairs, we will infinite chains of reductions. This is a nice trick in which you have to show how to build an enlarged context recursively from an infinite sequence of dependency pairs. Then from an infinite chain of dependency pairs, we are accumulating context in order to build the infinite recursion. Notice we have here the, okay, innermost reduction because our focus was to think about evaluation, Hegel evaluation, and reduction, but not arbitrary reduction, but innermost reduction. Okay, and to show that dependency pair termination implies a noetherianity of the rewriting system, then we do the same. We have an analysis by counter position, then from an infinite rewriting derivation, we have to build the infinite chain of dependency pairs. And this was done in the complicated part of the problem, how to build the infinite chains of dependency pairs from the infinite reduction. Then we have to extract some point of the infinite reduction in which we detect a rule applied in the root position, and this rule in the root position is used to build the dependency pairs. Okay, then the thing is that in the end, and I have talked for 50 minutes now, we have enlarged the PBS theory with 250 theorems, and we have this notion of correction of dependency, the notion of dependency pairs, the arbitrary notion of dependency pairs that is given by this K-restricted reduction. This is from René Tiemann also. And the proof of correctness of this reduction, that means, well, we prove that no seriality corresponds to the determination. Okay. And after that, we start to work on our objective. This is only a history to finish, no? The idea is, okay, we have this PBS functional theory, we have the term rewriting theory in PBS, and we have some criteria of termination here for the term rewriting system, and we want to use this criterion to show termination of functional programs. Okay, then the point is that the Kelling context graph are essentially, or follow essentially the idea of dependency pairs graphs. And then we start to think about how to do that. And we have to move from terms to values in the working type. And the thing is that we want to make translation from functional programming to rewriting systems in such a way that we have only non-conditional rewriting rules and first order rewriting rules. Then we have to transform wars into matching conditions. And for that, we make a restriction on Pressburger arithmetic conditions. That is only naturals with addition and less than equal. And we have a rewriting system for the Pressburger arithmetic. And from this rewriting system, we build the matching conditions. For instance, we have here a specification of GSD in PBS0. This specification checks whether the first argument is null, the second argument is null, whether the is smaller than equal the first argument, and we have then two conditions to check. Okay, in the four conditions. The first one is that since we are in the naturals, n is greater than 0, n is greater than 0, and n is smaller than equal than m, and so on. This is the else condition. And from the second condition, then we work with narrowing in order to extract automatically the matching conditions. Then for DS2, the conditions are built in a very easy manner. That is, essentially, M should be a successor, N should be a successor, right? And for this condition, less than equal NM with this sigma instantiation, the solution for the first one, then we work with narrowing in order to build the condition. The condition that we build is that M should be Sx plus Y and N should be Sx. This guarantees that the first argument is greater than equal the second argument. And the else condition, that is this one, also instantiated with sigma, works also through narrowing, providing the instantiation. That is, the first argument is SB, and the second argument is S from X plus SD. This guarantees that the second argument is strictly greater than the first argument. Of course, we have this restriction on the words of the programs, and we obtain a set of rules.
Sorry, just made almost time. We would like some time for questions.
Okay, then the thing is, I am finishing now. The thing is that we have some rewriting system, but this rewriting system should not use the rewriting rules. We use it for the extraction of the matching conditions. And we have to work with this rewriting system modulo the Pressburger arithmetic. That means we don't have this all the elements to reason about dependency pairs, okay? Because we don't have a theory of dependency pairs modulo that should be developed for that. An alternative is to use the Krauss et al. Mechanism that consists in extracting rewriting rules that are left linear and non-ambiguous. That means to build a rewriting system that is orthogonal. Okay, that is the synthesis we have in this PBS theory, some equivalent relation of the notion of termination. We have in the TERS theory some notion of termination, and we want to work in this direction. We want to integrate the termination criteria from term rewriting system in order to reason about a functional program. But we want to do that in a formal manner. That is the main use. Okay, I can finish now. I think I can put the case references from this talk, and sorry for talking more than 50 minutes.
So thank you, Mauricio. So are there any questions? If so, please feel free to unmute or raise your hand. You can also just ask it right away.
Can you repeat, please?
Sorry?
Whether you can repeat your.
I would happily start with a question if no one is raising their hand. So I noticed that you said that formalizing the recursion theorem is really similar to coding a computer virus. That wasn't quite clear to me how that works on slide 21.
Yes. Let's see. The thing is that the virus is encoded as part of the program. Then the idea is to you with this multifunctional program is that you add some additional part to the program. Then let me I try to go back to this. That is more the motivation. No. That was the key theorem here, because this is used for proving the Rice theorem. No, then the formalization is similar to programming a computer virus using a functional language with one difference. Okay, the partial recursive PBS program is processing its Gödel number. Okay, then at some point we are processing the Gödel number of the program. But the program is built, okay, the itself is built using the input program, that is the input program. With this notation, I am abbreviating the quadruple. And we have some print updated with the indices of this program, because we need to build a program so that the calls are consistent. Then the indices of the print are updated. This is the part that we say is similar to building to build a computer virus, right? And then with this trick, we have what we want. That's the evaluation of selves. Give us answer the Gödel number of self. Yes,
Okay.
it's because of that that we say that it's a construction of a computer virus.
Okay, thank you. Are there any other questions? Yes.
Yes. I would have a question, since we have now formalized several computability results for PVS0. So do you plan to extend this also to have complexity characterization, so that you show that somehow the evaluation mechanism is polynomially related to what needs to be done on a Turing machine or similar things like that?
Okay, that is an interesting point. In that we didn't talk about that, but this is an interesting point. No, we really were very attracted by the work on this library of undesability results from the group from Saarbrücken and Lorraine, Dominique Larcher, Bentley, and Yannick Forest. And we were planning to first start to prove things like post-correspondence problem undecidability and word problem undecidability and second order undecidability and things like that. What I think will be interesting from this point of view is to have a proof like undecidability of the decision of the Diophantine equations, the Hilbert-10 problem, and from that we will have a derivative, a lot of undecidability results. But this is other project, but because for doing that, you have to move from the functional program model. Then your point is interesting because reasoning about complexity maybe is something that might be done using the same PV0 model.
Okay, thank you.
Thank you for your question, René.
And the address of the discussion room is in the chat.
Okay.